All right, so here are some of the greenhouse gases that you're going to need to know. These are the primary ones that affect Earth's atmosphere. So at the top, these two are by far the biggest contributors. Methane being one that's also gaining more notoriety recently because there's a lot more studies being done on a relatively unstudied area of the planet, which is the polar north, where there's a lot of trapped methane gas in Arctic permafrost. So we had watched a video or listened to a podcast earlier in the unit that looked at methane and talking about how much of the calculations that we have used to figure out greenhouse gases in the atmosphere have not really taken into account the methane concentrations as well as the methane that might be emitted if some of the permafrost continues to melt. So either way, the two biggest ones at the moment are carbon dioxide and water, so CO2 and H2O. But methane, you're probably going to hear more of as we get better calculations, which just takes time. It takes researchers time to go out and perform a study and actually bring back that data and analyze it and see kind of what the effects are of methane on any given time period. But other things like nitrous oxide, ozone, which we had talked about, and CFCs or chlorofluorocarbons, all of these things affect the planet by warming or by trapping heat. And that's what they get their title, the greenhouse gas, from. Once again, these are the different chemical symbols for or chemical formulas for these different molecules as well. So as this is just a reminder of that. This is kind of what they look like from a molecular structure, or at least the model of how we represent them. So one of the things on page 10 in your notes packet that you're going to need to copy down. So there's a table there that talks about Earth's atmospheric composition. And on the right-hand side of that, in the double column notes, you're going to want to draw the pie chart that you see here. And the thing that is a little bit different from the pie chart that you're going to draw, as well as the ones that you see from the ones that you see here, is that you're going to actually include an additional slice for separating argon from the other composition. So on the right-hand side, you're going to draw a circle in the double column notes, and you're going to add these different levels for the different parts of the atmosphere. So let's go through those really quick. The first one, nitrogen, is the biggest component of the atmosphere. It's 78%. So N2 is making up most of the air that we breathe. And followed closely with that is oxygen. And so between those two parts of the atmosphere, that makes up 99% of the air that we breathe in. So every breath you take in, you're breathing in 99% oxygen and nitrogen. And then there's about 0.9%, all right, a little bit less than 1%, that's argon gas. So when you look at those three things, that makes up 99.9% of Earth's atmosphere. And so you might be thinking to yourself at this point, what is the big deal then? Why do we keep hearing about some of these other gases, carbon dioxide, methane, ozone, water? All right, why are they so important to talk about if 99.9% of our atmosphere is made up of these three gases, nitrogen, oxygen, and argon? Well, you're not wrong to be thinking that way because a lot of people did think that way up until the point that we started to understand what is a greenhouse gas. And at least part of that research, like we had talked about before, was done by the military when we were trying to better understand heat-seeking missiles back in the early days of the Cold War. And as they were starting to look at that, they realized that the heat-seeking capabilities of missiles were being affected by some of the heat-trapping components of the atmosphere, like carbon dioxide. And so they had to adjust for those aspects of carbon dioxide so that they could have better or more accurate missiles. So just kind of an interesting part of that history. And so with all of this, the gases that make up the final 0.1% of our atmosphere are gases like carbon dioxide, methane, nitrous oxide, ozone, water, and there's some other ones that are listed in here. So these three up here, nitrogen, oxygen, and argon, are not greenhouse gases. So in the table that you guys have in your notes. It talks about which ones are and which ones are not greenhouse gases. You're going to put a Y, or sorry, a no for these not being greenhouse gases. And then each of these down here are greenhouse gases. All right, so you'll put a Y for yes in these. And as you're drawing your circles, you're going to want to add in, like I said, one additional little piece of the pie. So here, this one shows you 78%, 21%, and then there should be a sliver in here for 0.9% for argon, and then the final 0.1% should say other. And that other includes all of these gases down here, as well as other trace gases. So for all of that, let's talk really quickly about some specifics of carbon dioxide. These ones we already discussed. So when we're talking about carbon dioxide, since it is such a minute fraction of the atmosphere, we actually don't usually talk about it in terms of the percentage. We actually talk about it in terms of the parts per million. So if you imagine a container filled with 1,000 marbles, or a million of some object. All right, you can think of marbles or Skittles. All right, well, out of those 1 million Skittles, all right, only about 421 by 2024 standards, only about 421 of those Skittles would be one particular flavor. All right, so it could be, let's just say, the green Skittle. All right, out of 1 million Skittles in that container, only about 421 of them are green Skittles, which means that that's the relatively small amount of molecules in each container of air that we might pick up in the atmosphere only are made up of that much carbon dioxide. But if we rewind the clock back to the 1800s, that actually changes closer to about 280 Skittles of that color, of green, back in that day. And the reason why that's significant is, once again, just the difference in how many of what percentage or fraction of the Skittles are now changed to the different amount of CO2 atoms. And so, CO2 molecules. And so all this increase is starting to show itself by noticing that more heat is being captured on Earth. Because remember, every time you see a heat-trapping gas that is a greenhouse gas, you're going to notice that more heat is trapped. That doesn't matter whether it's more water or more nitrous oxide or more methane or more CO2. All of those are like adding an extra blanket on the bed. And so the more of them you see, it's just adding an extra blanket and trapping more heat. And so once again, you're going to be measuring that in parts per million. In the 1800s, it was about 280. All right, we estimate it usually as about 280 to 278, and nowadays it's about 421. You do need to know each of those values as well. So these are just some of the approximate other measurements. You saw some of these on the simulator, and so like methane is measured in parts per billion because it's an even smaller fraction of the atmosphere. Nitrous oxide is also measured in parts per billion. So once again, these are very small amounts, but because of the fact that they have such strong greenhouse gas abilities to them, they still have an effect on the planet. They still actually do cause the planet to warm in a way that if they were absent, we wouldn't feel that same warming. And we're going to talk about this a little bit more later on. This is looking at some of the temperature aspects of what those greenhouse gases do as far as trapping heat. So thanks, good luck.